PDM is a new capability made possible by the next generation RPA platform, which is RPA+. This upgraded system includes a dye gap sensor, smart pressure regulator, and premier seal plates. But the real innovation lies in the dye gap sensor, a technology first introduced by Alpha Technologies and currently the only commercial rheometer on the commercial RPA on the market capable of measuring sample thickness in real time during testing. Here's why this matters. As a background, moduli G star, G prime, and G double prime are calculated by multiplying the measured torque, which is the only direct output of an RPA, by a geometry-dependent constant, which is C, and then dividing by strain, gamma. However, that constant, which is C, is directly affected by the sample thickness. Most commercial RPAs assume that sample thickness remains constant throughout testing, but in reality, that's not in the case, because especially during the testing, where shrinkage or expansion of the sample can significantly affect its thickness. This is where the dye gap sensor becomes essential. By measuring the actual sample thickness during the testing, PDM technology accounts for changes that will otherwise skew your results. And in our studies, we observed that PDM can reduce variation by as much as 50%. For example, in an after-cure SPR compound test, we compared the standard method, which is the standard commercial RPAs, with the PDM-enabled approach, which is RPA+, and the result, a 50% reduction in the coefficient of variation, just by incorporating real-time thickness correction. So in summary, PDM improves test reliability, enhances data accuracy, and brings a higher level of confidence when comparing materials that are prone to expansion, shrinkage, or batch variability. Okay, so now that we have covered the PDM technology available with RPA+, our next generation instrument, so let's wrap up with a bonus case study focused on shrinkage detection. So in this case, a compound passed all standard MDR tests without issue. Cure data looked normal. No significant differences in ML, MH, T10, T50, and T90 values. However, once the material was processed into final parts, it exhibited unexpected shrinkage and dimensional inconsistencies during production. To investigate this issue, we ran a standard isothermal cure test using the RPA+. As expected, it mirrored the MDR results, no significant differences in conventional cure parameters. However, what makes the RPA+ unique is its dye gap sensor, which continuously tracks sample thickness during testing on the right-hand side. So during the cure process, you typically expect a reduction in thickness as cross-linking occurs. And in this case, the dye gap data didn't show any major difference between samples during curing. So we moved on to a temperature sweep test, starting from 170 degrees C and cooling down to about 70 degrees C. So this is where the difference became much more clear. Compound B showed an 11% reduction in sample thickness as it cooled. On the other hand, compound A showed a 40% reduction, a clear indicator of shrinkage behavior that wasn't captured in the isothermal cure test. What is important here is that the dye gap sensor tracks thickness in real time, and those values are automatically integrated into the calculations of G prime, G double prime, and complex viscosity, giving you more accurate and more precise rheological data. At the same time, the thickness data itself becomes a direct diagnostic tool to assess shrinkage or expansion during processing, something not possible with traditional rheometers. This case basically perfectly illustrates how PDM technology and the dye gap sensor provide deeper insight into compound behavior, detecting real-world processing issues that will otherwise go unnoticed in standard cure testing.